Hi guys, I am Nathan with Good Mayhem Racing. Today we are going to do a complete change of scenery compared to what you usually see with me in the garage. I'd like to give you a brief update on something I've been working on. I've been working on a group buy. This group buy is for underlights on third generation 4Runners. You see these little turn signals underneath the headlights? Well, I designed a version of them that I like. I know there are products already available online, but I think I can bring some value to our community with the design that I have. And I have had wonderful feedback from other 4Runner enthusiasts. Toyota enthusiasts, to be more specific, I have installation instructions, different styles. If you'd like to see those details, feel free to check it out on my website or on YouTube. But there's a catch. It's just the starting point. 4Runners are cool and all, but the community is much larger than the third gen 4Runners. And one of the most loud voices in the feedback I have received for this mod are doing it for other cars, particularly the first generation Tacoma. So this is a video going into designing some underlights for first gen Tacomas. Thank you, random photo on the internet. I'm going to be modeling this little red filler plate underneath this really cool long travel Tacoma. I don't know what kit that is. I mean, I could give you a guess, but I got no clue. But if you can see his bumper, this bumper is the reason why I have been making underlights for third generation 4Runners, because when someone does an aftermarket front bumper for their Tacomas, they lose their turn signals. Just like any Toyota from the 90s, the turn signals are on the bottom part of the bumper. By relocating them up and high out of the way, you can protect them from damage, they look cool, and more importantly, they can help you stay street legal when you lose those turn signals. What was really cool about the Tacoma community as a whole is that they said, hey, here's a Tacoma, model it. So I have parts off of a first gen Tacoma. It is a 2002, and I believe the actual lights, the whole grille and fascia and bumper setup actually have wild design changes and design cues between the years, as in the stuff in the 90s probably won't fit the stuff from the 2000s and vice versa. So the first gen Tacomas are probably going to have 2, if not 3 unique underlight models to cover the breadth of all of those generations of vehicles. Like this right here, this 95 Toyota Tacoma, check how different the grille design is compared to one of the later generation Tacomas. That makes for a different underlight. Can the actual LED interface that I am designing work with all of them? I don't know, I think so. I mean, I'm kind of standardizing the way I'm mounting the LED lights. And the particular lights that I'm going to model for today are XK Glow switchback LEDs. I think that they are going to be the easiest lights to design around for the Toyota Tacoma. You can even see that in this photo that they have on their website. They have the third generation Tacoma with these things marked on the grill. Now we're going to put them in a cooler spot, and it's going to be on the first gen Tacos. Those cool lights you see right there are going to go on here. First, what software we're going to use for engineering? We are going to be using Solidworks. And you can see that I've already done some number crunching here. I'm going to rebuild that. I'm going to hide it. And we are going to start from a photo. No, actually, you know what? Take that back. Let's see that sketch. And I want to insert that photo in this program. So I'm going to Tools, I'm going to Sketch Tools, and we are going to find Sketch Picture. And this allows you to input a picture into SolidWorks, into the program. And I've already cropped and scaled a underlight trim piece, that filler trim piece for the Tacoma. And always import it on low resolution. If you do it on high resolution, the computer will hate you. I won't scale it right. The dimensions will be off. And you can see by my cool little box here that this thing is really big in comparison. My initial measurements, if I remember correctly, were that from this bulbous tip here all the way to the end. I'm going to try to right angle it right here. If I'm lucky, this blue line's going to be close. Nope, it is not close. Okay, that might be sheet metal. If it's just the sheet metal warping, great. Oh yeah, by the way, if you're going to like try to reverse engineer around a sheet metal body, realize like there's going to be a kerf to it. It's not even truly square, and that's something you're going to have to address. I'm going to measure this thing with a good old tape measure. If I had a pair of calipers that was long enough, I would use that, but I do not today. So whatever. I am right around 10 and 5/16. So 10 plus 5 divided by 1/6. Boom. That scale has changed. Let's move this over here and see how close we are in comparison to that little box I had earlier. Sorry, I cheated. The box was a happy accident. Let's get the pixels down to the borders. That is what is relevant for said design. And you can see a line that's going up here. Oop, sorry. Escape. Control Z. Nope, didn't take. Take it again. Go into this bottom corner, line it up, click away. Overshot it a little bit. I took an angle finder to this filler plate, and I realized that a lot of it is not square, as in it is inherently, by design, a few degrees off. So now we have to model our underlight around this front fascia. I'm going to hit Control B, or actually I'm going to hit check. Control B, Control save. Let's save this. I'm going to make a new folder here. Tacoma. Let's give it a drawing number, 0703-24-01, Tacoma Underlight. All right. So I have a photo here that you are looking at in addition to the dimensions I have measured earlier. There is a big problem with this photo in that it is probably skewed, as in I have a dimensional issue with a photo, parallax, not being truly square, the fisheye nature of the lens. Even though you and I can look at this object and recognize it for what it is, bets on that when you try to one-to-one dimension it inside the computer program, it's going to be physically twisted one way or another, as in this object is not truly flat or square to the plane that you are sketching on. Gonna hit rebuild. Now let's push this in front of the other sketch. So sketch 2, this is the photo. We're gonna rename these here. Sketch number 1, this is going to be the front plate. Control B, Control save. If you're a nerd, you can do Control Q. That rebuilds everything and tells you if you're stupid or not. But let's hide the photo. Look at this line up here, this blue one on the top right corner. Let's see if it lines up with the body line of the filler plate. It does. It's pretty good. I was measuring that earlier, and I realized it was not truly square. It was like 2 degrees off. There's probably a manufacturing tolerance to whatever Toyota originally engineered. However, I don't know what those tolerances are, and I don't have access to those prints. Those are from the 1990s, and now I am working off of hearsay. And what's interesting is that in this photo, it appears like this is sloped much more than it actually is. So if I take the front plate and I edit this sketch, when I measure the physical real part, as in when I take my angle finder to the top border of this thing, when I measure it out, it looks like it's only dropping a degree. It's like almost square, but not. And visually you can see it taper down, right? But it's only like a degree. So I have 89 degrees there. So that means that this image is really off compared to what I need to design for. So even though I can make a cool little spline shape here and then start nailing some curve or detail of this underlight, it's probably going to have to change based upon the real dimensions I measure. That semicircle you see right there is actually a spline, as in a curve, a mathematical curve between a couple of points, in this case 3. I'm going to zoom into this corner here where I've got my 2 degree marker. I'm going to intersect that line and make the spline tangent to my line. All right. So if we ignore the rear photo, you can see that the shape of the underlight is already forming. Some things that I need to respect, though, are these edges. Since they're not part of my part, I need to make them construction lines, things to make details around rather than dimensions. Whenever you're dimensioning the part, you want your real lines to be the relevant criteria, not the construction lines. If you did it by the construction lines, you would have an interference point. And this right here is a classic example of that. You can see how these two things don't line up. Well, just because I measured 2 degrees, or a single degree actually, like 89 degrees rather than 90 for that top corner on the real physical part, I need to make that match not the right angle here, but the angle that's from here. So there's a physical tolerance stack that I would be ignoring if I didn't use that instead. So this is going to be a construction line now. I'm not going to delete it yet, but I do need to know that it's there, because the real 89 degrees is based upon that line there. At least I thought so. I can measure that part again. This one thing was 2 degrees inboard. This next thing was a degree in. Yeah, it's only a degree. I'm using a Starrett miter cut angle finder for this. If I do 90, let's see what that looks like. Let's look at my photo. 90 actually lines up with that really good. I might have a parallax problem with my photo, but that is actually lining up really well. 90 degrees off of that 2 degree cant is like rock solid onto the line that we have here. I don't know. I'll have to physically print a sample out and see how close it is. Doesn't feel right. Be that as it may, now that we have some line that is remotely matching the content that we have here so far, let us trim this stuff here. So you and I are going to trim this line off. Now you see how this box became gray? Now it's a complete body that you could extrude out of. This corner though is a little rough. Let's look at the photo again. It's got this real nice corner taper to it. Let's make that happen. And sure, my measurements are probably going to be practically off somewhere, but right now we're just trying to make a part and we're trying to see how close we can get it. It's okay if it's not perfect right now. This needs to be trimmed. Might hate myself later for that. We shall see. This spline needs to be tangent to this line here. All right. You see how that's starting to fill itself out? Well, we can't. Now, let's check all of our shape. Make sure we got no surprises. This needs a radius corner here. I do have radius finders with me, radius gauges to be more precise. I can eyeball what that radius is right now. My gut is telling me it's a little less than 1/8, but it's a little more than 332. So if we're doing that in millimeters, maybe 3 millimeters. So let's take this and this, and we'll tell it a unit 3 millimeters. Don't capitalize it, because then it'll be 3 megameters. Let's do the same down here. Yep, that's actually matching very nicely. So that makes me think that they probably spec'd it around 3 millimeters originally. I don't know how to do a 3 millimeter check here. This random circle that I just made, I'm not trying to line up everything here, but 6 millimeters is the diameter. And let's just move it around. See how close it is. Not close. It's definitely bigger than that. I'm going to hide my photo here because it's causing me issues with my program. Oh, nope, my spline is just disappearing. Groovy. Lovely. It's not supposed to do that. We're going to make that a construction line. This and this need to talk to each other, so we're going to make them coincident. And I'm going to tell these two splines to play nicely, and that did not go to plan. I told them to be tangent, and I'm pretty certain I just ruined the flow of my model. Yep, I did. Undo, undo, undo. All right. I don't like what I have here, but I don't have something better. Oh, nope. I'm going to fix this point at the risk of over-defining my sketch. Undo. I'm going to fix this line here. Stop it from moving. All right. Now we have forced this spline into submission. Not perfect, mind you. Let's see how close we are now compared to our front plate. And suck it up in. Sucking this down. Okay, we're a little low. Bring that back up. I'm not a fan of this corner. I can probably force this thing to become a fillet of some kind. A random 3mm fillet, and that's pretty close. Okay. Check. Control B. Control save. Always save your work after a big operation in Solidworks because this program is famous for crashing. Famous, I tell you. All right. The sheet metal of the part is very thin. Like the physical sheet metal itself is a very thin gauge. It's only like 1 millimeter thick. That's tiny. That is tiny. But the actual breadth of it, when you take the sheet metal part that's been bent, that's pushing around what? 6, 7, 8.5 millimeters. So we're going to extrude this thing. We're going to bring it out of its little hole a full 8 millimeters. 8.5 millimeters. Okay. Again, save. I am the saving meister. Control S, Control B, Control Q, rebuild, and save. Just for grins, we're going to include the radiused edges on this thing, and they seem to be pretty close to 1/8 of an inch. Some tells me they're a little bit smaller than that, so we are going to go back to the venerable 3 millimeters for our radius. Let's apply this fillet. Going to tell it 3 millimeters, and we're going to boop it. All right, do you see all of these yellow profiles all around? These these hashed lines around the blue. That is my fillets. Cool. We're going to hit save. Let's change the background to plain white because that makes everything easier to see. And I am a perspective guy. I know a lot of people will provide or be shocked by that, but I don't know. Like whenever I do perspective off on a program like this, I kind of forget how everything is really sized, even though you're seeing the true parallax-free, perspective-free sizing of everything. It's just weird when it's not an isometric view. Okay. So I've got this, and it's cool, it's useful, but I need to find out if it is true and relevant to my actual part. So I'm going to hide the drawing. We're going to screenshot this part. Or actually, you know what? We might be able to just straight up print it. Control P. See what we can do. Preview. Okay. 8.5 by 11. That's the size page I've got. And this part certainly fits on 8.5 by 11. Barely. Okay. Close. Control P. Properties. I don't remember this part. Bear with me here. "3D printing, what's up with that?" Oh, that's cool. Hold up. I got distracted. Verify the print volume dimensions. Select a plane to face the model or rest on the bed, then set the 3D printer options. Oh. Oh, that's cool. Well, okay then. I'm going to learn that later. Let's suppress this fillet. Let's roll it back. If I'm going to be doing this on a 3D printer, I guess we could do this with 3D printing instead of a physical paper printer. I'd rather use paper printer just because it's so easy and so fast and squirts out. But if something's wrong with the scale, you'll be able to find out very fast if it's accurate or not with a 3D printer. Okay, so let's do this relatively thin. Let's do it 2 millimeters thick. We're gonna remember that 8.5. Tell you what, 2 millimeters. Check, build, save. All right. So this is how thin our object is. Let's file, save as. Solidworks can output as a step file. Save that. Bamboo Studio. Let's pull that up. It's a little gun shy right now. Okay. Let's create a new project. Let's import a part. And let's go down to the folder that we made earlier for the Tacomas. Let's drop in the underlight. And let's orient this part. That is a lot smaller than the Forerunners. That's really cool. Okay. Well, I shouldn't have a problem printing these. That's encouraging. Control B. Oh, no, that didn't work on this program. Save. Save. All right. For this little 2 millimeter thick article, you can see that's going to cost 44 cents worth of material. That doesn't include energy and engineering time and all that. And it's going to consume 17 grams of filament. Cool. So I will print this out physically later on the 3D printer to compare it to the real life sample that's in my hand right now. Well, let's close this program. Get back to this. All right. Let's change this extrusion back to 8.5 millimeters. Check. Unsuppress the fillet because it looks cool. Now we have the back side of this thing. And that is the next part of our little engineering challenge. Save. The document cannot be saved with an empty sketch. Rebuild and save document. Okay. Turn off perspective because we are now sketching. Dimensions are more important than looking cool. The article has 4 mounting points that clip into the sheet metal tabs that made up with the grill. So we need to have 4 random pieces of material here that are going to represent the sheet metal tabs as they mount to the truck. Nothing has to be perfect right now. Right now we're trying to just get a good control on where the holes need to be for this, not the shape of the tabs themselves. What I mean by that is the holes have an absolute point, right? Like when you physically take a hook and hook it through a hole, that hole has to be of a certain size. Everything around it is optional. 2 degrees, I don't like that. That point up there was really convenient. I want to see if I can whack it. There's a point. There's a point. Now I can dimension off of this point for this here. Great. We're going to dimension the offset of this. Over here, we are going to dimension imperfectly. I don't know. if this sheet metal tab is parallel to the top face, then what I'm doing here is wrong. But I can force it to make them parallel. See how this went red? That means it's overdefined. I have to delete this relationship to make that work. Kill the horizontal, and now we have that. Kill the horizontal. We're just going to take this entire one here and move it down. You can make all three of these lines. Oop, nope. I tried doing something a little too fancy here. Kill the horizontal. Kill that parallel. Alright. Kill this horizontal. Let's match these up. Cool, that one actually worked. This one, not so much. Let's kill that horizontal. Make parallel. Great. All right, so those two are parallel with the top face of the underlight, and the two on the bottom are already inherently square with that one. To measure the sheet metal from the bottom, sorry I don't have a photo of myself here. That would have been really, really cool right about now. To measure the offset height for that, the bottom of these sheet metal tabs are 0.193 inches away. Whoa, my bad. All right. 0.193 inches away from that surface. This one here is probably different. Just because something looks the same doesn't mean that it actually is. So let's measure. Whoa, I fell through there. They're close. I don't know. That actually makes me think they are the same. Because I've got like 0.215. These are in inches now because I'm just faster in that. The sheet metal itself was, with its coating, a little over a millimeter. So we're going to call it a millimeter. 1 millimeter. And we can do that everywhere here. 1 millimeter. 1 millimeter. 1 millimeter. Okay, the width of each one of these slots is probably standardized. They're probably all very close, if not the same. Bottom corner one, right now, if we are millimeters, we are at, I don't know, it actually kind of matches American a lot more accurately than it does metric. Whatever. All right, we are at 0.625 inches. We are at a full 5/8 width. That does not round up to a metric number at all. And now the top one, though, that one's a lot more of the exact same thing. Was this truck designed with metric or American in mind? Asking for a friend. 0.625. What the heck? 624. I mean, I'm a thousandths off of like 5/8. Let's measure this bottom one here. Point 623. I'm just going to round that up again, 0.625. Because I'm dealing with a coating where these guys wouldn't have at the fab stage, 0.625. Now, look very closely, and you're going to see that the 0.63 on the right is actually tilted compared to the 0.63 on the left. they are actually measuring two different dimensions. One of them is measuring the horizontal dimension. The other one is measuring the parallel dimension. So you see that? 5/8 this way, 5/8 that way, 5/8 this way, 5/8 that way. I'm measuring it compared to its respective surface, 0.625. It's going to scratch it up a tiny bit. In this particular instance, because everything's off by only a couple degrees, it's only a few thousandths of an inch. But that can be a problem when you are actually doing really complicated parts. From the face, right now these things are right around, oh, it's in millimeters this time. I got 2 millimeters. Don't worry about like trying to convert the units while you're doing this stuff. Just type in the raw unit and it will do it for you. So like you can see everything's in inches right now. Just squirt in the 2 millimeters and boom, it becomes 0.0787 inches. It's kind of nice. Oh, we gotta measure how and where our holes are compared to their counterparts. I've got a bit of a tolerance issue there for the square, but okay, whatever. I've also got an issue because the actual mounting plates are at an angle compared to what I've actually got here. So I'm going to have a bit of noise that I'm just going to have to accept. Hold up, I gotta think. Like physically, it doesn't come out. Like if I were to just extrude this right now as like little slots like this, that looks all nice and pretty, but really they come out at an angle, like straight down if you were to look at this view. So what I'm doing right now is really wrong. So I made a mistake there. So even though I've got the right idea for the holes, like where they would go, because they're on the wrong plane, I am wrong. If I can measure that plane, I will make it. We're going to hit Control B. We're going to be right back. Let's make a plane. Reference plane can be off of that. Second reference. Cool. I've got a fully defined plane here and it's wrong. Can't use it. Let's delete this edge. Control B, Control Save. All right, I got to figure out how to get this angle into this part. Let's do a three-dimensional sketch. So we can lay this out. So I'm doing a pseudo coordinate system out here. Trust me, it's not perfect. tab, tab again. All right, now I've got a line. Let's measure this line in comparison to its brethren. What angle must this be? Again, sorry I don't have the cool little streaming view setup that would be necessary to actually show you guys how I'm doing this. But my reference only dimension right now is a little over 15 degrees. It's really close to 16. Gonna try to do it on 16, see how that looks. It's not great. It's 15. This plate is curved. Okay. All right. Okay, so the Tacoma's surface is actually curved, like the actual face. It looked really flat to begin with, but it's got something going on. We're just going to call this 15 degrees for now, and we're not going to worry about that. My fillet is garbage, so we're going to delete that. Now that we are on this top view right here, I need to make a curve. If I take a spline here, take it to this outside edge, heck, any edge for that matter. Let's go randomly to the middle, come back down. All right. So now I've got a spline here that looks like a curve. We don't know if it's the right curve, but it is a curve. Fortunately, my stuff is not snapping to that for some reason. The bottom is the part that I considered square earlier. I should probably be doing it on that surface rather than the top one. So we're just going to delete my happy accident there. Go to the bottom. Sketch. Okay. Try this again. A spline. That's more like it. Now I'm snapping correctly. I don't even know if it goes to the middle, you know? Like, this is a curve that I genuinely don't know what the value is. When you have a flat surface, you can calculate the gap that is produced by a curve. This spline. And right now I've got 0.308 inches. I don't know, that rounds up really nicely to 8 millimeters. Okay, so 8 millimeters divided by 4, or 8 millimeters divided by 2 is 4 millimeters. So let's tell this thing that this is a 4 millimeter offset here. This top of the curve is on the very top of it. Okay, 4 millimeters again. I don't know, is this thing really on the top? It's close enough for what I'm going to do. Boop. Boop. I'm just going to cut it. I really don't care if my little cut line's perfect. I'm just trying to delete stuff, you know? extruded cut through all both. Well, that's annoying. My curve has a flat spot. That means that my spline wasn't truly on the line. Let's go edit it and check it. Zooming in, zooming in, zooming in, zooming in. No, it's there. It's on the line, all right. Okay, we will respect it for what it is. We'll match it up on that midpoint. Control B, Control Save, and I will just accept the flat spot. All right, so now we have a curve on our face. It doesn't look weird. It looks kind of normal. And now we have all of these extra little plane details based upon this flat face that we have here. And for everyone who's watching now, just thank you so much for taking the time to check this out and be interested, because I think it's cool. At the same time, this is no easy feat to design something. So I am just going to call it a night at this point, and we will continue on at a later date. And thank you guys so much for watching. I will see you out in the desert, if not my garage. Here is the first video demoing the underlight for the Tacoma. Catch you laters.